All right, everybody, welcome back again, and let's see where we are here now. We took values for received power and we plotted them on this graph, and we got the standard deviation, and we generated this central processing unit algorithm or protocol where the central processing unit of the robot would be able to take a value of received power, say 6, and convert it into a percent of aperture opening. And then we made the suggestion to use ratios of received power in order to solve the problem of preventing the central processing system from being confused by random variations of the output power of the transceiver that was the source of the signal. And of course, one of the things that we need to come back to, people I'm sure would say, yeah, well, this is a great plan, except remember, you're not supposed to be using values down here in the 10 to 20 to 30% aperture opening area, because you begin to get into quantum mechanics, power distribution patterns that don't lend themselves to good measurement. So over here, for example, on the robot, if we're going to be calculating a ratio, and here is the piston that's moving back and forth, and we'll go down here to this situation where the piston 1 transceiver is in the zone where most of the output of the piston 1 transceiver is going into cylinder wall transceiver channel D, and the piston, say, has moved where now 90% of this power output is coming into channel D. 10% of the piston 1 transceiver power is coming into channel E. And you may have a question of, well, if we're going to calculate a ratio, how are we going to calculate a ratio if we're not supposed to use values where the transmitted power coming through is of such a low amount that, and that's F, let's get E here. That we're seeing quantum mechanical effects. And so now we are in a quandary because we're supposed to be using ratios. So, you know, D here would be at the 90 to 100% power level, but E would be showing quantum mechanical effects. And that's a type of ratio calculation that's going to be hard to do because of the considerations that we made over here. And so that is one of the problems that we're going to see with this ratio of power calculation protocol. And we are going to also, before we get into the solution for this, we're going to address another issue, which is that if you have simply a aperture opening value of 60%, for example, if you come over here and look at this piston, one of the even if you're in the zone of the piston that we have considered to be an acceptable zone for power value measurements. Right here, let's say the piston is at 30% of opening. And so the piston is in that location. It's shifted in the direction of E. But a problem exists in that this is also exact from a power output viewpoint with respect to D. This is also at the 30% level, so that simply a note of percent of aperture opening is not going to distinguish between an aperture opening of 30% where the piston is shifted. Let me rephrase that. A aperture opening of 30% for cylinder wall transceiver D can have two different configurations of the piston. This is a 30% opening of the doorway for cylinder wall transceiver D, but this is also a 30% opening of the doorway for cylinder wall transceiver D channel with respect to piston transceiver 1. So we're going to address those two problems. If we can get those settled, then we have a good system for measurement of the position of the piston.